Hello all, welcome back to SEMM3023, Applied Numerical Methods. In my last video, I think we were talking about root finding or roots of equations. And I think I did mention something about this one, which is the approaches that we can do for finding our roots. Okay, so one of them is bracketing, graphical, and open method. So I think in the previous video, I showed you how to solve this graphically. Basically, what we did was to plot FC. Okay. So with respect to plot FC with respect to C, and this is what we get. So we noticed that when the line or the function intersects the x-axis, this is where the root is, right? So, and if we zoom in, it is about 14.55, 14.55. And yet, if you look at the solution, FC equal to 0.49. But if the solution is correct, FC should equal to 0. So the problem here is, do we accept this kind of error, or do we not accept this kind of error? So let's go back and see now. In this video, what I'm going to do is to talk about the bracketing method. So we'll be using the same equation, which is this one, but we are not going to use graphical method, but we are trying to use what we call the bracketing method. So let's go to the new set of slides. Okay, and this is the one. Okay, so root of equations. We did the graphical method before, and now let's move to a new approach, which is bracketing method. So let's go. So the content of this video is about the bracketing methods concept, different cases of two guesses, graphical approaches, bisection method, algorithm, and then we can see the graphical depiction of bisection method, the evaluation of the method that we are using, is it good, is it bad, and the number of iterations required to get the solution. And there's one more, which is the incremental search algorithm. And I'll be showing you both the bisection methods and the incremental search method. Okay, so the bracketing methods, okay, the concept is we must have two initial guesses. Okay, two initial guesses, which means two initial guesses for the root are required. These guesses must bracket or be on either side of the root. For example, in our case, okay, this is our C and this is our FC, and we note that our root is somewhere here, 14 point something. So in this case, what we need to know is we have to have two guesses. Okay, one on the left hand side of the root and the other on the right hand side of the root. So for example, let's say this is 12 and this is 16. So this is one bracket and this is the other bracket. Okay, so basically the root is between 12 and 16. How do we know there's a root? Notice that for, let's say this is lower. This is lower limit. So let's say x at L, or in this case, C lower and C upper. Okay, so C lower is the left hand bracket, C upper is the right hand bracket, and we note that in this case, F for CL is positive and F for CU is negative. So the product of that result is a negative number. So we know if the two brackets values are negative, then if the two bracket values, if the product of the two bracket value is negative, then there exists a root between the lower and the upper guesses, right? So then we say that then okay, if one root is real, if one root is a real and continuous function, fx equal to 0 is bounded by value x equal to xl and x equal to xu. So the lower bracket and the upper bracket, then we know the function of the lower bracket times the function of the upper bracket must be a negative number. So positive, negative. So there's a root between these two brackets. There are also, it can also be like this. As long as, and this is, let's say, x lower, and this is x upper. Okay. So as long as there's change of sign, or the product is negative, then we know there's a root in between the two brackets. So this is the concept. So we need to look for change of sign. We need to look for a negative sign for the product of the two, for the function of the two brackets. Okay, then we know there's a root in between. So this is the concept. Right, so for example, in our case here, root for FC is between 12 and 16. So this is the one, 12 and this is 16. So there's a root here, right? So CL equal to 12, lower, upper limit for C is 16. So sorry, lower bracket is 12, upper bracket is 16. Then FCL is a positive number, right? This is a positive number. And FC upper is a negative number, which is here. So the product of these two functions is a negative number, or I can just simply put less than 0, which is the same thing as a negative number. Okay, so this is the concept. Again, the product of the two brackets, the product of the two functions of the brackets must equal to a negative number in order to for root to exist. So let's take a look at some other possibilities here. So yeah, if we have both are positive signs, for example, and there's no root, right? Both are positive sign, so there's a possibility of even number of roots, 2 roots here, 2 roots. Okay, so this one has no root, this one has 2 roots. It has 2 roots. Okay, and then in this case, we have different signs. One is negative, the other one is positive. Then definitely there will be at least one root in between the two brackets. And in this case, again, the same case, one is positive, one is negative. So we have odd number of roots here, odd number. So 1 is odd, 3 is also odd. Or if we have 2 roots, then the possibility is that both are positive. Both are positive. So these are some issues. So if you just want to find one roots, you need to make sure that your bracket is, for example, this is one bracket that you can use, or you can also use this bracket. So you have one minus and one positive. So these bracketing methods can only find one root at a time, provided that the bracket is correct. Okay. So this is another issue here. We have one positive, one negative. Okay, but this is just on the tangent of x. Sometimes using numerical method, you cannot find this because it might not be touching because of the error. So this is one possibilities. Okay, and the other case is this is discontinuity. So if your bracket is too big, you might not be able to find the roots. But if your bracket is this small, then you can find one, and this small you can find the other one, and the same thing here. Okay, so these are the bracket. Remember that bracketing method works best to find one roots, provided that your lower and upper bracket are correct. So how do we know the bracket? So the best thing is to use a graphical method to basically estimate. A simple method for obtaining an estimate of the root is draw a plot. Okay, nowadays drawing a plot is easy. Just plug in the number in your Excel or your MATLAB, then you can see. So if you look at this, we have from 0 to 5, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This might be possible, 13 and 14. 14 roots between 0 and 5. So be very careful. Which one do you want to find? Okay, so at least this will give you an idea. There's one between this bracket. Okay, there's one. There's one between, there's another one. There's another one. And so you need to do, basically find the correct or the appropriate bracket for each roots. Okay, so now let's move to the next slide. Okay, we are going to talk about bisection method, bisection method algorithm. Okay, so it has all this: choose X lower, X upper, and so on. So I think you can read this. What I'm going to do is to give you an example. Okay, we are going to use bisection method for our falling parachetes example and see what are the results. Okay, so when we do this bisection method methods, we know that I'll show you what happened when we do this calculation, and then the pro and cons. Okay, the pro and con, and the number of iterations required to do to get the up to the right precision. Okay, and then this is the calculation, and after that we will go to the incremental search method algorithm. Oh, I think I missed this one should be a method here, incremental search algorithm. Right, so let's look at my example. Okay, before looking at my example, let's go back to this algorithm, which is not this one, but this one, the bisection method algorithm. So it says here, choose lower XL and upper XU guesses for the root such that the function changes sign over the interval. This can be checked by ensuring that fxl times fxu is less than 0 or a negative number. Okay, so let's go to my Excel spreadsheet here. Okay, so this is the same as your quiz. Okay, so the question here is that G is given, oh, okay, my G is wrong. So G should be 9.81. Okay, so M is 68.1, B is 40, T is 10, and error, stopping error is, we stop the iteration when the error is 1 to 10 to the power of minus 6. Okay, so the first step before we can use bisection method is to make sure that we are using the correct lower and upper bracket. So how do we know? So let's try with lower as 12, okay, and upper as 13. Okay, it says that my interval is bad. Why? Because there's no root. Look at this. This is a positive number. This is a positive number. And the product of these two functions is a positive number. So there's no roots. So that's why the interval is bad. Let's try with a different XU. We can keep trying. So let's try with 14. Okay, still not good. Try with 15. Okay, then it's good. Say that this is good. Okay, so for the sake of just an example, let me try my XU equal to 16. Okay, equal to 16. Okay, just like this example here. Just like this example, where we use, where is the, oh, not this one. Okay. Okay, this one. 12 and 16. 12 and 16. Okay, so let's go back to the slide. Okay, so we know lower bracket 12, upper bracket 16 is a good guess. These are the two guesses, 1 and 2. So we have a negative numbers, and we know that our interval is good. Okay, our interval is good. So we can put here 12. Okay, and we can put here u. Sorry, upper limit is 16. Okay, so let's look at this algorithm again. It says here that the algorithm says we done with step 1. So this is 12 and 16. So estimate the root XR. An estimate of the root XR is determined by XR equal to XL plus XU over 2. So in this case, 12 plus 16 divided by 2. Okay, so 12 plus 16 divided by 2, which is 14. So if you take a look at my spreadsheet again. Okay, so this is the one, B14 plus C14 divided by 2. Right, so the next step is, it's here already, it's here. Okay, so make the following evaluation to determine which subinterval the root lies. So fxl times fxr. So we need to times these two values and to see if they are negative or positive. If negative, then the root lies in the lower subinterval. Okay, so in this case, this is a positive number, so this is the explanation here. If the product is a positive number, the root lies in the upper interval. So my Excel already tell us that this is a upper interval. Okay, so after that, if the root is if the product is positive, the root lies in the upper subinterval, which is upper interval. Therefore, set XL equal to XR. So my new XL must equal to the previous XR, which is 14. So this is my new XL. Now is 14. So my bracket now is 14 and 16. Okay, let's take a look graphically what happened here. Okay, let's look graphically what happened here. So let's go to this paper here. Okay, so bisection method. Bisection method. So it says that, what we have is a root, and I have, this is my 12, this is my 16, right? So my XR is 12 plus 16 divided by 2, which is 14. So take a note that this is XL, XU, and this is my XR. Okay, so what happened is my FXL times FXR is positive. Why? Because this is positive, this is positive. So there's no root in the lower interval. So the root lies in the upper interval, right? So this is the root. The root is between 14 and 16. So this is what happened to my Excel sheet. It says that the root interval is the upper subinterval. It's not in the lower interval, because in the lower interval, the product is positive. So now set the new lower interval or the lower bracket as 14. The upper still remain the same, which is 16. So now my new interval is this one. So now this become the new. So this is my first. This is my first iteration. This is my second iteration. So this is XL now, and this is XU, and of course the new one is XR is somewhere here. So we check if FXL times FXU positive or negative. In this case, it looks like, FXL times FXR, it looks like there's a root in between, right? So this is negative, then we know that the root is in the lower. The root is in here between these two. So let me draw this. Here, this is the first interval. The second interval, okay. The second interval become, okay, the second interval become like this. So now the second interval, the second iteration, it become something that looks like this. Okay, so this is 14. Now this is 16, and 14 plus 16 divided by 2 is 15. So this is 15. This is my XR now. Okay. Sorry, before this, my 14 was my XR. Now my 14 become my X lower, and this is X upper. So we find the FL times FXR, and definitely this is positive, this is negative, so this is negative. So root is somewhere here. So there's a root at the lower interval, but there's no root at the upper interval. So let's take a look at my Excel here. So notice that the new XL is 14. The upper remain the same, and XR is 14 plus 16 divided by 2, which is 15. And FXL times FXR becomes a negative number. Then we know the root is in the lower interval. So now what happens is that our lower remains the same, but our upper bracket is 15, right? So if you take a look at the drawing again, you see that now this become the new upper bracket because the root is somewhere between this and this. So this is my second iteration, and my third iteration will become something that look like this. Okay, so this one. So this is 14. Now this is 15, right? Before this 15 was XR. Now 15 is XU. So this is XU. This is XL. Then XR is 14 plus 15 divided by 2, which is 14 and a half. This is 14.5. Okay, 14.5. Between, let's look at this one. So this is XR. Okay, so FXL times FXR equal to, so this is positive, so this is more than 0, positive, which means that root is in the upper subinterval. So this is the area of interest now. This is the interval of interest. So now at the fourth iteration, then this is 14.5. This is 15, and we have something like this. So now this is our XL, this is still our XU. So we need to find a new XR. So what is XR? Equal to 14.5 plus 15 divided by 2. So I think you get the idea here, right? So what you need to do is take the XR and then evaluate the lower subinterval to see if there's a root. If there's a root in the lower subinterval, then you move the change your upper limit XU to become your XR to become your new XU and so on. So this thing is in loop. So you need to do this multiple times. You need to do multiple times. Let's take a look at here. Now we know that my root is in the lower interval. The new XL is the lower bracket is 14 and 15. So this is the error. So we'll talk about error later. Okay. So let's copy this. Okay, I don't have a mouse here. Okay, so this is not as easy as I hope. Okay, so let's move to the next iteration, which is number 3. And you see that now, okay, lower interval is 14. Sorry, the lower interval is still 14, but the new is 15. So XR is 14.5, and we know that the root is in the upper interval, so we change the limit. All right, so now let's try and do this until we get the required accuracy or precision here. Okay, so let's do this. Let's try maybe a few iterations at one go. Okay, after 6 iteration, the error is still 0.4, but to be able to stop, the error should be less than 1 to the power of minus 6. So we are not yet getting the right one. So okay, this is where if you look at the slide, tell you how many iterations that we need. So this is just what I did just now. Okay, this is what I did. So our first guess was XL, and then this is our XU, and this is our XR. So we know that during the first iteration, the upper subinterval is where the root is. So we move this. So we move this. We use this subinterval for further calculation. So this is 14. Now this is our. Note that previously this was XR. Okay, this is 14. Now 14 become our XL, and this is our XU, and this is our XR. So 14, 15. So we know that there's a root in the lower interval. So we take this interval and we do more calculations. So this is now our XL, and previously 15 was our XR. Now 15 become our XU, and this is our XR. So we keep repeating. Right, we keep repeating. So the question is, how many times do we need to repeat? Okay, so I hope you can see now that the methods is easy. You can always find a root as long as the first step. Okay, as long as you have confirmed the first step. So the first step was this. The first step was this one here. Okay, the first step was this one. So we make sure there's a root in between the lower and upper bracket. So I have found this. Okay, I have found this. Right? I found this. Okay, now let's continue. Okay, the number of iteration required to attain in absolute error can be computed a priori. So we can have a priori mean beforehand. Okay, we know the value before the current iteration. So we can calculate the iteration. Okay, because remember for the following parameters, when we did the analytical solution, we have a priori information. Okay, for example, v equal to 0 at t equal to 0. So this is what it's meant by a priori. From the word, this is I think Latin, but the English word is prior to. Okay, so they call it a priori. Okay, this is the pro, but the cons, it is slow. Okay, we already repeated 6-7 times and we still have not get the solution. Okay, no A and B that bound the root. So we need to know what is the lower and what is the upper bracket. Okay, so I think I did mention about we need to at least have the graphical method to assist us where the root are. Okay, so we can also have multiple roots, but we are using only one bracket. So remember this? Remember this? Okay, or remember this? Okay, one is positive, one negative. We thought there's a root, but there are multiple roots. So again, this is why we need at least a graphical methods to help us identify the range where the roots for the roots. The range for the roots. Okay, so multiple root. No account is taken of fxl and fxu if fxl is closer to 0. You know that for roots, the requirement is fx must equal to 0. Right? But sometimes when we calculate xl equal to maybe 0.01 and fxu equal to 0.5. Straight away, we know that this one is closer to the solution. But when we are using this bisection method, we ignore this fact. We didn't take this into account. So no account is taken for fxl, and if fxl is closer to 0, it is likely that the root is closer to xl. So this is close to the solution, to the roots. But when we do our bisection method, we ignore this fact. Okay, we ignore. So that's one of the cons. Okay, that is one of the cons there. Okay, now this is the number of iteration needed. The number of iteration needed. Maybe we can do some calculation and see if the number of iteration required match our calculation. Okay, so let's go back to my Excel. My Excel sheet here can give us the information needed in order to calculate the total number of iteration needed for this example. So I mean, for the requirement that the error must be smaller than 10 to the minus 6. Okay, so let's go to the slide. Okay, so this is the number of iteration required. Okay, the total number of iteration required. Okay, the number of iteration required for the calculation. So in our case, we need to know what is L0. So L0 is just B minus A, or in our case, it is just XL minus XU, which is 16 minus 12, which is equal to 4. Okay, so which is equal to 4. So we know that our L0 equal to 4. Then after the first iteration, L1, then our L0 is divided by 2 because we need to find what is our XR. So XR is just XL plus XU divide by 2. So we have by 2. And then after that, for the second iteration, we divide L1 by another 2. So which is now 2 divided by 2. So now this one is basically L2 is equal to L1 divided by 2, or L0 divided by 4. So this is L0 divided by 4. Now after k iteration, this is the formula. So k is the number of iteration. K is the number of iterations. We can work this out. We can work this to find what are the number of iterations required for our problem. So the other thing is, let's talk about what is EA and what is ES. Yeah? Sorry, not E, but epsilon. So epsilon S is the stopping requirement, error for the error limit. So error when this accuracy is achieved. In our case, our epsilon S equal to this one here, 10 to the minus 6, 10 to the minus 6. So in our case, this is equal to 1 to the minus 6, 10 to the minus 6. And what is EA? Epsilon A, sorry, epsilon A is what we call the approximation error. So how do we calculate approximation error? Okay, how do we calculate approximation error? So approximation error is this one. If you recall from your error analysis slide, so I think this is the one, right? So this is the approximation error. Approximation error. So what we'll do is, because we are doing this iterative calculation, then the current approximation minus the previous approximation, everything is divided by current approximation is 10/100 is the approximation error. And let's see how I implement this formula in my Excel. So let's look at the Excel. Okay, let's look at the Excel sheet here. Okay, so this is my error, right? This is my error. So if I look at this is the formula. Absolute value of D15 minus D14. D15 is this one, which is the current approximation minus the previous approximation divided by the current approximation. So current approximation minus previous approximation, everything is divided by the current approximation times 100%. So this is the error. This is the error calculation. So this is the error calculation. Okay, so that's how I implement the approximation error. And our calculation will stop when this is achieved. So when this is achieved, so we need to keep calculating until EA is less than 10 to the minus 6. 10 to the minus 6. And let's take a look at our current position now. Our current position now, we are at 0.4, which is 4.2 times 10 to the minus 1. So we are very far away from basically getting the result that we want. Okay, so do we need to stop? No, because this is 0.4. The requirement is 10 to the minus 6. So we are very still far away. So I hope you can imagine how much more iteration we need to do. Okay, if you are doing this by hand, it will take you forever to finish this. Luckily, we have Excel. And luckily, you can also do a programming for this one. You can also do a programming for this one. Okay, now let's see. Let's try to estimate how many iteration that we need for our problem here. Okay, let's take a look at the formula. So this is the formula. This is the formula. So we need to use this. We need to use this formula. Okay, so if take a look at the next one. So this is how it's calculated. So this is just one example. In our case, our L0 is not 2, but our L0 is 4. Our L0 is 4. Okay, let's take a look. Let's try to do this. Let's try to calculate this again and see how to get the solution, how many iterations that we need to get this solution. Okay, So let's go to this piece of paper and try to solve the problem. Okay, the requirement is epsilon s, sorry, not epsilon s, the other way around. Epsilon A must be smaller or equal to epsilon stopping. So in our case, our epsilon s is 10 to the minus 6 and our EA equal to what? Remember just now, what we have is EA, basically new root minus old root or minus old root divided by new times 100%. Right, that is our approximation error. And this can be simplified. Basically, new minus old is just our L. Okay, and after a few times, what we get is 2 to the power of k. K is the number of iteration. And of course, this is the new root, right? So we have to have, let's say, x is our root times 100%. So we know that our EA is equal to L over 2k x times 100%. Okay, so this is similar to the slides, which is this one. But I think this is from the textbook. I think this one should not be n, but this one should be x, or the root. Okay, the root. Okay, now the next thing to determine is what is ES. Okay, ES is 10 to the minus 6, right? ES is 10 to the minus 6. And if you look at this next page, this is the one. So this is the relation between ES, sorry, not ES, epsilon S. Okay, and let's try to do this, to solve this. Okay, so our stopping error is when error in x, okay, when error in x is less than 10 to the power of minus 6. So how do we calculate this? Okay. Okay, before we continue, I think this one should be L naught, right? L naught. Okay, and let's double check this formula. Okay, L naught over 2k, right? So, which is correct. So now let's continue with the with sorry, not E, epsilon S, the stopping. And we know that the numerical value for epsilon S is 10 to the minus 6, but in terms of x, in terms of the root, what is epsilon S? What is epsilon S? Okay, so we need to find the relationship between epsilon S with the root x. So how do we do that? Okay, so the first thing, what is meant by 10 to the minus 6 error? So error in x, error in x, okay, so let's do this. Let's delete this. ES is basically defined as when error in x reach a certain value. For example, in this case, in x is 10 to the minus 6, right? So what is this? How do we write this? So the error is, okay, and of course, in terms of percentage. Okay, so let's write this here. So error in X is less or equal to 10 to the minus 6%. Okay, in percentage. And note that this can be any value that you want. So in our case, in my problem, this is 10 to the minus 6. So what is this? What is error in X? What is error in X? Okay. So what is error in X? So we can calculate error in X as X times ES. So when the error is 10 to the minus 6, which means the 6 decimal place or the 7 decimal place has error. Other than that, it's okay. So X times 10 to the minus 6 is the error at the 6 decimal place in this case. Okay. And because this thing is in percentage, so we need to divide by, in percentage, then this become less or equal to 10 to the minus 6 percent. So this is what we call the error in X. So when we reorganize this, what we can say is that 10 to the minus 6 can be written as X epsilon S divided by 100. Okay, divided by 100. Okay, so now let's go to the next page. We know that our EA, not EA, epsilon A, sorry, keep saying that is E, and actually it's not E, it's epsilon A equal to L naught over 2 to the power of K times X times 100%. And the requirement is that to stop the iteration, what we need here is when EA is smaller or equal to 10 to the minus 6. So EA, epsilon A, is L naught over 2K times X, 100%, should be less than 10 to the minus 6. But what is 10 to the minus 6 in terms of epsilon S? So it is just this, X times I think there's something not right here. Let me double check what is wrong here. Okay, what is wrong here is that my algebra is wrong. Okay, so 10 to the minus 6 is just X times oh, sorry. ES is this one. I'm not trying to find what is 10 to the minus 6. I want to find what is ES actually. Epsilon S. Epsilon S is less greater than 10 to the minus 6 times 100% over X. Okay, over X. So that is where I did wrong. So let's write that here. Let's write that here. So our epsilon S formula is just 10 to the power of 6 times 100% over X, over x, and we did this comparison. So the comparison is that the stop iteration epsilon a must equal, must be less or equal to epsilon s, and epsilon s is 10 to the power of 6, 100% divided by x. Okay, so there's something that we can do here. We can eliminate x. We can eliminate 100%. So this reduced to L naught over 2k less than or equal to 10 to the power of 6. Okay, 10 to the power of 6. Okay. Okay, this is similar. This is similar to the formulation. Yeah, so this is similar, where this is the error, epsilon s, and this is your L naught, and this is 2k. So this is the same formula that we get for our case. So let's do this. Let's try to solve this. Okay, so we know that our L naught is equal to 4. L naught equal to 4. And when we substitute this, we get 4 over 2 to the power of k should be less 10 to the power. Oh, okay, this is minus 6. I think this is minus 6. Let's double check. Okay, so this is minus 6. For some reason, my minus went away when I transfer the. So this is minus 6, minus 6. Okay, 10 to the minus 6. Okay, and let's try to solve for k. Solve for k. And in this case, we know that 2k should be greater than 4 times 10 to the power of 6. Okay, so how do we solve for k? So in this case, what we can do is to take the log to the both side. Take log for the both side. And so let's do this. So this is log 2k greater than log 4 times 10 to the power of 6. Okay, and we can solve this. So how do we solve this then? K should be, okay, let's do the long way. K log 2 greater than log 40,000. So log, this is 40. Is it 40,000 or 400,000? I think 400,000. 10 to the power of 6. No, this is 4 million. Okay. 1, 3, 4 million. Okay. And we can solve for k. K should equal, should be greater. K should be greater or equal to log 4,000. Sorry, 4 million divided by log 2. Not this is, take note that this is log base 10. Log base 10. So k should be greater or equal to, let's do the calculation. Okay, let's do the calculation. This is equal to 6.60206 divided by 301.03 times 10 to the power of minus 3. So this is around, what is this? So k should be greater or equal to divide by log 2 around 21.93. So iteration k, iteration should be greater, iteration k should be equal or greater than, okay, the iteration k should be greater or equal to 22, at least 22. Okay, at least 22 iteration for our case to get EA equal to 10 to the minus 6. So 22 minimum iteration needed for 10 for epsilon A to be equal than 10 to the power of minus 6. Okay, so let's try and see. Let's try and see if we get the answer. So 22, at least 22 iterations, at least 22 iterations. So let's go to the Excel sheet here. Okay, so we have done only 6 iterations, so we need a lot more. We need a lot more. So let's do this. Let's do this and see. Okay, highlight this and then drag this thing here. Okay, drag this thing. Okay, so all right. So note that up to 22, our absolute error is 6.4 times 10 to the minus 6, right? So it is good enough approximation, but to stop the iteration, we need this absolute error, this error to be less than 1 times 10 to the minus 6. This is 6. So if you look at this is still 1, which is greater than 10 to the minus 6. So this is 8.05, 10 to the minus 7. So it stops at 25. See, so this is the stop. But what is the results here? What is the value here? So let's see. Let's see what is the value of C, because I think I miss dragging. Okay. Okay, so there's a value here. So is there a value? Okay. Okay, here. So we need to drag this. Okay. Okay, so we need to drag that. Okay. Okay. Okay, so drag more. Okay, up to here. Okay, it's 14.8. 14.8 0.113. So this is the solution here. This is solution 14.8. 1.14.8011.359 is the solution. So let's look at this this value here. Okay, it is very close to, this is basically 0 now. Basically 0, because this is 2.99 times 10 to the minus 14 times 10 to the minus 14. So a lot of zeros there, a lot of zeros. Okay, so this is when 1, this is when the error stopping requirement is 10 to the minus 6. If you look at the slide, they use 1 to the minus 4 and see how many iterations needed. So in this case, it requires 19 iteration to stop. Okay, 19 iteration. But if you look at the absolute error, 10 to the minus 4 is about 18 iterations. About 18 iterations. Okay, so let's take a look at the slide. The slide is using 10 to the minus 4, and the iteration needed is about 15. But okay, the iteration needed is about 15 when error is 10 to the minus, when the stopping error is 10 to the minus 4. 10 to the minus 4. But what we get for 10 to the minus 6, so it's slightly off. It's slightly off. The calculation get 15, but when we did the iteration, it requires 19. It requires 19. Okay, it requires 19, and the case for 10 to the minus 6. Okay, it requires 25 iterations. 25 iterations. So our prediction is about 22. It's about 22, but note that should be greater or equal than 22. So once you reach 22, there's a possibility that you can get the right number of iterations. The right number of iterations. So the actual iteration for this case is 25 iteration. 25 iteration. So this is how you basically estimate the number of iteration needed for this kind of problem. Okay, let's continue. Why don't we look at the slide and see? Okay, so this is the, I think what we did just now was calculating the number of iteration needed for our bisection method. Okay, so this is basically giving us a rough idea how many iterations we need. Okay, so now I think in our case we have to use, when we calculated, we get 22, but when we run the calculation, it requires at least, it requires 25 iterations to get, to stop the calculation. Okay, so the next slide, okay, is about the incremental search method. Okay, incremental search method. So let's do this. So this is another bracketing method. It has the same concept. Basically what we need is, again, it is said here that the value of x is incremented by delta x from an initial value of x1 successively until a change in the sign of the function is observed. Why change of sign? Because when you hit a change of sign, means you have you have found the root. You have found the root. The root is in your, basically your bracket. Okay. Okay. The only problem with this incremental search algorithm is that when delta x is too small, it will be time consuming. You have to do a lot of calculations. Okay. When delta x is too big, you might miss a closely spaced root, which means sometimes they have two roots and the two roots are close together. And if your delta x is just too big, you might miss that second root. Okay. Or you might miss both of them at the same time. Okay, so this is another issue. So what is the algorithm for incremental search method? First, set an initial guess for x I equal to 1 and step size of delta x. So let's try to do our problem again. So let's try to do this. So for incremental search method, okay, let's try with this one. Incremental search method. And we know that we have a root at somewhere here. And I think this is around 14.8. Around 14.8 from our previous calculation. Okay, so let's say our x I equal to 1, x1 is equal to 12. And let's say delta x equal to 6. Then we know that our x2 is equal to 16, just like our bisection method, where in our case, in bisection method, we have, if you recall, then x L equal to 12, then x, not delta, x u equal to 16, right? So we are using the same parameters here. So start point is x12. Sorry, x1 is 12. Delta x is, okay, delta x is not 6, but delta x is 4. Then x2 is 16. Okay, so in this case, what we're trying to do is, let's do this. So this is 14.8. And then we have, let's say this is 12. Okay, 12 and 12. 13, 14, 15, 16. This is 16. Okay, this is 16. And okay, so that's one of the requirements. So we know our xi, our x1 is 12, delta x is 4, and then x2 is 16. So we need to find what is this value of f12 and f16. Okay, so let's look at the algorithm again. It says here that set an initial guess for x I equal to 1 and a step size of delta x. Call the function of fx to calculate its value at x equal to 1. So we know it's a positive number. Okay, increment, then this one is 12. Sorry, this is 16 because this is 12 plus 4. This is 16. And then call the function fx to calculate its value at the second point. Okay, compare the sign and return the function value to the previous xi. Okay, so let's take a look. So in our case, we know this is a positive sign. This is a negative sign for 16. Then we know there's a root in between. So what we'll do when we find a root? So now we say that this is our first iteration. Okay, and then this is our second iteration. So what we'll do for our second iteration is, okay, if the sign does not change, repeat from step 3 again. Okay, if does not change, then we have to increment. Okay, if the sign does change, the root lies between x1 and x2, which is in our case. Reduce step size delta x and set the new x equal to the one before and repeat step 3. Okay, so in this case, what we do here is, since there's a change, then our new x1 equal to 12, but our delta x is now reduced. Okay, reduced. So in this case, just like our bisection method, we reduce it by half. Okay, so now this is 4. Now this is 4, which is 4 divided by 2. Now this is 2. So our x2 now is 12 plus 2, which is 14. Which is 14. So if we draw this again, okay, if we draw the curve again, what we have here is, okay, so this is 14.8. This is 12 plus delta 2. This is 14. So this is positive. This is positive. So there's no change, right? There's no change. There's no root. So what we'll do if there's no root, so if the sign does not change, repeat step 3. So we increase again. We put an increment. So now there's no sign change. Then x2 is equal to 14. Delta x still the same. And then now x3 equal to 14 plus 2, which is 16. So if we do this, what we get now, and this is 14.8. Okay, this is 15. This is 16. And this is 14. This is 14. So if you can see that this is positive, this is negative, there's a root. So the first step, the first step now, x1, repeat because x1 is now, we go back to 14, x1 equal to 14, and delta x now equal to 2 divided by 1, 2 divided by 2 equal to 1. So now, it becomes, if this is 14.8, then let's say this is 15, then our x1 is 14, this is 15, then there's a root here, right? There's a root. So there's a root. So, okay, this is 15, then there's a root because this is positive, this is negative, there's a root. We go back by half. Now our this is 14. X1 is still 14, but our delta x equal to 1 over 2. Now x2 equal to 14.5. So this one is x2 equal to 15. So it's getting closer and closer to the root. So you repeat this until you can stop. Okay, until you can stop by using the same method as bisection, which means you need to calculate the epsilon A. So we stop when epsilon A is less than or equal to epsilon S. Okay, let's say our epsilon S is equal to 10 to the minus 6, and we need to calculate sigma A. So let me show you my Excel spreadsheet using the same algorithm. Okay, this is bisection. This is bisection method. So let's try this one, incremental search method. Okay, so what we want to do is our x1 is 12, and our delta x is 4, just like our previous example, which is bisection. Okay, so what we found is x1 is 12, x2 is 16, and we look at the sign. So f, the function, when x equal to 12 and the function when x equal to 16. There's a sign change, right? Yes. So we need to reduce the delta x. So in this case, I reduce it by half. So 4 divided by 2 equal to 2. And the new xi is still 12. So 12 plus 2, 14. So this is the new one. So let's take a look at this one. So this is the first one. This is the first iteration. Okay, this is the first iteration. So this is the second iteration. So it's 12 and 14. And then it go to 16. So 12, 14, and 16 because this one has no root in between, but the second one has a root in between. So let's expand this Excel. Okay. So look at this. Our EA at epsilon A is still more than our ES, epsilon S, which is not stopping. So what we'll do is we just copy this, drag this, and see what is the value. So take a look here that the sign change, right? The sign change. So after 7 iteration, so our error is still 0.49. So do we need to stop? No. So we need to continue again until we hit the stop indication. So let's go. So this is 7. Okay, so this is 20. And note that the error now is 9 times 10 to the power of minus 4. Okay, if you remember, just now from bisection method, our calculation requires, I think, 25 iterations, right? So this is already 20 iteration, and our error is still huge, which is 9 to the power of minus 4. So let's continue and see how many iterations. By the way, the formula that we just used is not applicable for the this method. That formula is only applicable for bisection method. Okay, so let's try this and see. Okay, after 29, the error is 2.972 times 10 to the minus 5. So we are close. We are close because we need to hit less than 10 to the minus 6. Okay, less than that. So let's do this. By the way, it's already more than the bisection method because when we are using bisection method, the total number of iteration needed was only 25, but this has been more than 25. So let's go more and more calculation. Okay. Oh, still not. So after 34 iteration, still okay. Still does not achieve the target. But take a look at the absolute error now. It is very close to less than 10 to the minus 6. Okay, maybe a few more, maybe 2 or 3 more iterations, then we can hopefully get the value. Okay, let's do this. Okay, so it stopped at iteration number 36. Okay, it stopped at iteration number 36. And look at the result. The result is 14.8011355. And compare that with the bisection methods. So 14.8011359 and 355. So if you look at the error requirement is 10 to the minus 6, which means it will be accurate up to 5th decimal places. So 1, 2, 3, 4, 5, which is 3, 3. Okay, so up to 14.801, 13, we are good. So compare this with this bisection method. Okay, 1, 2, 3, 8, 0, 1, 1, 3. In this case, if you round this, okay, this is the whole solution, 14.8011359. If we, if we round the incremental search method, it become 18.80114, which is the same number as bisection. Or if we go to up to 6 decimal place, which is 135, if we round this, it become 135, 136. 136, and this one is the same thing, 14.80113. So look at the solutions here. So we notice that either we are using incremental search or we are using bisection method, we get the same answer. But the only issue here is that when we are using the incremental search method, it requires 36 iteration to get the same accuracy as bisection method. Bisection method only requires 25. So it seems that bisection method is converging faster than incremental search. So if you do this by hand, you have to do 8 more. Sorry, is it 8 more? Because 25 to 12 more. 12 more calculations, which might be time consuming. So okay, so these are the results for our problem, our parachutis problem, using two different bracketing methods. Okay, one is bisection method, the other one is incremental search method. So okay, with that, I think we have reached an end of our topic here. So until the next video, thank you very much.